Today, I'll present our study on energy harvesting using sloshing motion. We compared several magnetic arrangements to determine which generates the highest induced voltage. Sloshing naturally moves magnets without mechanical linkage. By placing a coil on the tank wall, the changing flux produced electricity. Prior studies used simple arrays with limited flux by variation. We tested more advanced arrangements to enhance efficiency. Sloshing increases fluid motion when the tank is vibrated, especially near resonance. This amplified movement drives our magnet array. We use this passive, re- repeti- repetitive motion as the energy source. Induced voltage dependent on how quickly magnetic flux change. Therefore, field direction, geometry, and polarity patterns strongly affect output. Optimizing magnet arrangement is essential. Different arrays create different field patterns, directional, alternating, or multiple. Flux change rate differs greatly among them. This directly determines induced voltage. We built a sealed tank with a 100-ton scale coil. Magnets float on styrofoam to maintain stable linear motion. A linear stage drives left-right sloshing under fixed conditions.
Passport sensor recorded real-time voltage waveforms. We analyzed peak amplitude, mean magnitude, and consistency. Multiple trials were taken to reduce noise. We test first standard linear, and second alternating NS cross, third Harbaugh array, and lastly fourth scalar ring. Each produces a distinct magnetic flux distribution. The linear array produces the lowest output about plus minus 2.5 millivolt. Flux spread is wide and flux variation during motion is small. The cross array alternates polarity, causing rapid flux reversal. This led to the highest output, around plus minus 25 millivolts on average. A strong periodic flux reaching maximized EMF. The Harbaugh array concentrates flux on one side. Performance depended heavily on alignment with the coil. Downward focused about plus minus 8 millivolt and side focused about plus minus 4 millivolt. The scalar forms a closed magnetic circuit and multiple field. Its low output was plus minus 18 millivolts, normalized to plus minus 9 millivolts for magnets. 3D flux variation improves coupling efficiency.
Here is the overall comparison. The linear array had the lowest voltage, and the cross array was the highest because of the polarity changes rapidly. The Harbaugh array worked only when its focused field aligned well with the coil. The scale ring showed strong output due to its 3D flux variation. So again, the key factor is the rate of flux change. The cross array works best because it creates fast, repeated flux reverser, and this maximizes the change in magnetic flux and produces the highest EMF. The Hubble array is very direction dependent. If the focused field isn't aligned with the coil, the usable flux drops a lot. That's why its performance varies. The square ring reduces flux leakage and creates multiple variation. This 3D motion increases flux change frequency and improves coupling. The table shows the average and peak voltages. The cross array clearly has the highest efficiency among all configurations. Thank you.